Hello everyone, I'm Farhad from ECE, C section. Today in this presentation, I'm going to talk about the rise of quantum internet. Before jumping into the topic, let's have a look at what are quantum devices. A device whose functionality or principle of operation depends essentially on the quantum mechanical effects is called a quantum device. A large number of devices already function based on the control of quantum mechanics. Quantum mechanical phenomena where a particle, electron, or hole, in the case of STM measurements, tunnels through a barrier that it could not overcome within the laws of classical physics, interactions, or effects. What is quantum internet? The quantum internet is a network that will let quantum devices exchange some information within an environment that harnesses the weird laws of quantum mechanics. In the quantum world, data can be encoded in the state of qubits, which can be created in quantum devices like quantum computer or quantum processor. In simple terms, we can say that it involves sending qubits across a network of multiple quantum devices that are physically separated. Qubit. A qubit or a quantum bit is the quantum mechanical analog of a classical bit. In classical computing, the information is encoded in bits, where each bit can have the value 0 or 1. A qubit is a two-level quantum system where the two basis qubit states are usually written as 0 or 1. A qubit can be in state 0 or 1, unlike a classic bit, in linear combination of both states. This phenomena is called superposition. The two orthogonal Z basis states of a qubit are defined by 0 and 1. The qubit basis states, we implicitly refer to the Z basis states as the computational basis states. The two orthogonal X basis states are The two orthogonal Y basis states are. Let us have a look at the diagram. The basis states are located at the opposite points on the block sphere representation of the state of a single qubit. Block sphere. It is a unit 2 sphere with antipodal points corresponding to a pair of mutually orthogonal state vectors. The north and the south poles of the block sphere are typically chosen to correspond to the standard basis vectors 0 and 1 respectively. The points on the surface of the sphere correspond to pure states of the system, whereas the interior points correspond to the mixed states. It may be generalized to be an n-level quantum system, but then the visual is less useful. Bits. It's a single unit of information that has a value of either 0 or 1. Let us know the difference between bits and qubit. Bits. The device computes by manipulating those bits with the help of logical gates like AND gate, OR gate, or NOR gates. Qubit. The device computes by manipulating those bits with the help of quantum logical gates. Bits are used in classical computers while qubits are used in quantum computers. Information is stored in bits, which take the discrete values 0 and 1. In a qubit, the information is stored in qubits. A qubit can be in states labeled 0 and 1, but it can also be in a superposition of these states a into 0 plus b into 1, where a and b are complex numbers. Let us look at an example of bits. If storing one number taking 64 bits, then n numbers take n times 64 bits. For example, in a qubit, if we take for every extra qubit, we get to store 2 times as many as numbers. For example, with 3 qubits, we get coefficients for 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, and 1, 1, 1. Bits are slow, qubits are way faster. Its circular behavior is based on classical physics. Its circular behavior is based on quantum mechanics. Qubit notation. Classical bits always have a completely well-defined state. They are either 0 or 1 at every point during a computation. There is no more detail we can add to the state of a bit than this. To write down the state of a classical bit, see we can just use these two binary values. For example, C is equal to 0. This restriction is lifted for quantum bits. Whether we get a 0 or 1 from a quantum bit only needs to be well defined when a measurement is made to extract an output. At that point, it must commit to one of these two options. At all the other times, its state will be something more complex than captured by a simple binary value. Mixed state. A pure state is fully specified by a single ket. Psi is equal to alpha into 0 plus beta into 1, a coherent superposition represented by a point on the Bloch sphere. Coherence is essential for a qubit to be in the superposition state. With interactions and decoherence, it is possible to put the qubit in a mixed state. A statistical combination or incoherent mixture of different pure states. Mixed states can be represented by the points inside the Bloch sphere or in the Bloch ball. A mixed qubit state has 3 degrees of freedom: the angles theta, psi, as well as the length r of the vector that represents the mixed state. Let us know about quantum entanglement. It is one of the uber bizarre phenomena seen when things get itty-bitty or inside the quantum realm. When two or more particles link up in a certain way, no matter how far apart they are in space, their state remains linked. That means they share a common unified quantum state. So observations of one of the particles can automatically provide information about the other entangled particles regardless of the distance between them. And any action to one of these particles will invariably impact the others in the entangled system. Discovery of quantum entanglement. Physicists developed the fundamental ideas behind entanglement as they worked out the mechanics of the quantum world in the early decades of 20th century. In the quantum world, nothing is ever known for certain. For example, you never know exactly where an electron in an atom is located, only where it might be. A quantum state summarizes the probability of measuring a certain property of a particle, like its position or angular momentum. They found that when two particles are strongly correlated, they lose their individual quantum states and instead share a single state and a unified state. They found that if two particles are entangled, meaning their quantum states are strongly coherent and become unified, then the measurements of one of these particles automatically influence the other, no matter how far away the particles are from each other. The first physicist to use the word entanglement was Erwin Schrödinger, one of the founders of quantum mechanics. He described the entanglement as most essential aspect of quantum mechanics since its existence is a complete departure from classical lines of thought. What is EPR paradox? The Einstein-Podolsky-Rosen paradox is a thought experiment proposed by physicists Albert Einstein, Boris Podolsky, and Nathan Rosen, with which they urged that the description of physical reality provided by quantum mechanics was incomplete. The paradox involves two particles that are entangled with each other according to the quantum mechanics. The EPR description involves two particles, A and B, which interact briefly and then move off in opposite directions. According to Heisenberg's uncertainty principle, it is impossible to measure both the momentum and the position of the particle B exactly. However, it is possible to measure the exact position of particle A, and by calculation, therefore, with the exact position of particle A known, the exact position of particle B can also be known. How to create a quantum entanglement? There are many ways to create entangled particles. One method is to cool the particles and place them close enough to each other so their quantum states overlap, making it impossible to distinguish one particle from other. Another way is to rely on some subatomic process like nuclear decay, that automatically produces entangled particles. What can quantum entanglement be used for? Perhaps the most widely used application of quantum entanglement is in cryptography. In this scenario, a sender and a receiver build a secure communication link that includes pairs of entangled particles. The sender and the receiver use the entangled particles to generate private keys known only to them that they can use to encode their messages. If someone intercepts the signals and attempts to read the private keys, the entanglement breaks because measuring an entangled particle changes its state. That means the sender and the receiver will know that their communications have been compromised. Another application of entanglement is quantum computing, in which large number of particles entangled, thereby allowing them to work in concert to solve some large complex problems. For example, a quantum computer with just 10 qubits can represent the same amount of memory as 2 to the power of 10 traditional bits. What is quantum entanglement teleportation? In quantum entanglement teleportation, the information about one quantum state is transported to great distances and replicated somewhere else. First, a sender prepares a particle to contain the information they want to transmit. Then, they combine this quantum state with one of an entangled pair of particles. The receiver then records the change in the entangled partner of the pair. Finally, the sender must transmit via normal channels the original change made to the entangled pair. This allows the receiver to reconstruct the quantum state in the new location. Here is an example of quantum entanglement teleportation. Thank you so much.